Okay, some of you may have been curious. Why is it that the limit as theta goes to 0 of sine of theta over theta, why is it that this limit equals 1? Well, considering the following picture here, notice I have drawn in an angle of some theta, and we can assume that this theta is positive and sufficiently small to put it in the first quadrant so that the picture matches up with our description. And you'll see I've also drawn in some triangles here, a small shaded reference triangle for angle theta, and a larger right blue triangle formed by just extending this tangent to the circle and this line right here. Okay. Hopefully, no one would disagree if we said that the area of the small red triangle was less than or equal to the area of the sector of the circle here, shown in green. I'll write that as area of sector, which in turn is less than or equal to the area of this larger blue triangle. So that's the bigger triangle. Okay? That should be patently obvious just by looking at our illustration here. Now, let's try to find expressions for each one of these three areas in terms of theta. So first off, the area of the small triangle. Well, notice from here to here, this of course is the cosine of theta. And in a like manner, from here to here, that must be the sine of theta. Okay? So the area of the small triangle, base times height over 2, would then be sine of theta times cosine of theta over 2. Okay? That, of course, is less than or equal to the area of the sector of the circle. Now, how do we find the area of the sector? Well, remember, we have used theta radians out of a total possible 2 pi radians to get the area of the entire circle. So it looks like this sector should represent theta over 2 pi times the area of the entire circle. Of course, this is a unit circle, and so the area is pi times the radius squared, or pi times 1 squared, or simply pi. Okay, and we'll clean that up in a minute. We can certainly simplify that. But this, in turn, is less than or equal to the area of this larger triangle, shown here in blue. Now, how do we get the area of the larger triangle? Well, the base is easy. It's a unit circle, so this segment here is 1 unit long. We just need to come up with this height. Let me call that h for the moment. But notice that this big blue triangle and this red triangle are similar triangles. And so this side is to this side as this side is to this side. So h is to 1, remember it's a unit circle, is the same as this side is to this side. So sine of theta over cosine of theta. Of course, that tells us identically h is sine of theta over cosine of theta. Matter of fact, we'll just erase that out there and just replace that with just an h. Okay, so that's my height. My base, of course, is 1. Just multiply those two and divide by 2, and it looks like the thing that should go here is sine theta over cosine theta, and all of that divided by 2. Of course, I'm going to accomplish the same thing just by putting a 2 in the denominator right there. Okay, so let's clean things up a little bit. We have sine of theta times cosine of theta over 2 is less than or equal to, of course, here the pi's cancel, and I'm left with theta over 2 is less than or equal to sine of theta over 2 cosine of theta. Now you may notice there's a lot of 2's here. So one thing we could do is multiply the entire string inequality by 2 to clear all of those out. But I'm going to actually do more than that. What I want to multiply by is 2 over sine of theta. Okay, so I'm going to multiply by that. That's going to get rid of all the 2's. It's also going to get rid of these 2 signs, although we will pick up another sign in the middle term in the denominator. Okay, so if I do that across the board here, that sign and that 2 go away, so I'm left with cosine of theta. Here, the 2 goes away, but I pick up a sign in the denominator, excuse me, and on the right, the sign and the 2 go away again, and I'm left with 1 over cosine of theta. Okay, so now is when things get interesting. Notice this theta over sine of theta looks very much the same as this. It's just upside down. Okay, and that was by design. That was one of the reasons I multiplied by this 2 over sine of theta, not just to get rid of these 2, but to actually manufacture an expression that looked very, very similar to this. In fact, it's just the reciprocal. So what I want to do now, given the fact that this is trapped between cosine of theta and 1 over cosine of theta, for all sufficiently small positive values of theta, again, that puts us in the first quadrant, I want to consider what exactly is the limit as theta goes to 0, again from the positive side, of cosine of theta, and the limit as theta goes to 0, again from the positive side, of 1 over cosine of theta. So that's what happens to this piece and what happens to this piece for small positive values of theta. Well, these are no surprise. Cosine is a continuous function. We can plug it in. The cosine of 0 is 1. And in the same manner, 1 over cosine of theta is continuous at least at 0. And so we can plug in again and get 1 over 1, or 1 as the value of the limit. So in the limit, as theta approaches 0 from the positive direction, this expression gets arbitrarily close to 1. This expression gets arbitrarily close to 1. This is always trapped between those. And so we then know that the limit as theta goes to 0 from the positive side of theta over sine of theta must also be 1. Okay? Now we're almost done. Remember, we want the general limit as theta goes to 0 from either direction. But notice theta over sine theta, or sine theta over theta, either one you want to look at, is an even function. Okay, so its behavior coming in from the right, that's this, and the behavior coming in from the left, in other words, what happens when theta approaches 0 from the left of theta over sine theta, should also then be 1. Okay, taken together, the limit as theta approaches 0 from either direction of theta over sine theta is 1. And finally, reciprocating, the limit as theta approaches 0 from either direction of sine of theta over theta must then be 1 as well. Okay? And that right there is what we intended to prove. I'll put in a couple implication arrows here just so you can follow the flow. But that's it. QED. We're done. That is why that limit is a 1.